The Francis Elizabeth, a bottom trawler operating out of Plymouth, Massachusetts, is setting sail for 12 hours of fishing.
25 knots this afternoon and 10 to 20 knots tonight.
With the calm sea and clear weather, the crew is hoping for a good yield, but success is by no means guaranteed. Total yield depends on many factors. How deep is the water? How many other vessels are competing for the stock? How many fish are available?
We'll go another half a mile.
As soon as they pass the legal limit, Fisherman Dave goes out to prepare the net. Once the net is in the water, the crew can do nothing more than hope for a good catch. Every other boat on the coast is out to do the same thing: catch as many fish and make as large a profit as they can. But how many fish can be harvested without depleting the resource? That depends on how large the population is and how fast that population grows. Understanding how populations grow can be as important to the success of a fisherman's business as deciding where to cast his net. A fisherman's livelihood also depends on the growth of another kind of population: dollars in the bank. Money and fish are related. Mathematically, they both grow in the same way. Dave plans to open a savings account with $100. Naturally, he wants his money to grow in the fastest way possible. What kind of account should he choose?
Hi.
Hi, how you doing?
Good. I'd like to open an account, but I'd like to get some help to figure out which kind is right for me.
Do you have any particular account in mind?
Well, I think savings.
In order to make the best investment, Dave needs to understand how interest is compounded. A compound interest account pays a fixed rate of interest at specified intervals. Compounded annually means that after the compounding period of 1 year, interest is added to the original deposit called the principal. Say Dave puts $100 into an account that pays 10% interest compounded annually. Dave's balance after 1 year would be the principal, $100, plus 10% interest, or $10. The same equation stated another way: 100 times 1 plus 0.1 equals a new principal of $110. At the end of the second year, he'll earn 10% interest on $110. So we multiply his first year's accumulation by itself. A shorthand way of expressing the same formula is 100 times 1 plus 0.1 squared. When we work this out, we come up with a balance of $121 at the end of the second year. At the end of the third year, we go through the same process. Multiply the term we used to figure 2 years' interest by itself plus 10%. So now the exponent is 3. At the end of 3 years, Dave's new balance will be $133.10. This continues for as long as he leaves the money in the account, so at the end of 5 years, say, his final balance will be $161.05. In a compound interest account, interest is earned on interest. So every year, although the interest rate remains unchanged, Dave will earn more money than he did the year before. Mathematicians call this kind of increase geometric growth. Now that he understands how compounding works, Dave has other factors to consider. Here are the accounts this bank offers, each with its own interest rate and minimum balance. And there's another thing he should think about: how frequently the interest is compounded. Let's see what happens if he puts his $100 in an account that compounds interest not annually, but quarterly, every 3 months. Interest rates are almost always stated on an annual basis, so for shorter periods we need to divide the rate by the number of periods in a year. So if Dave deposits $100 in January, at the end of March he'll earn 1/4 of 10% interest, or 2.5% interest, on his $100 deposit. His new balance will be $102.50. At the end of June, he'll earn 2.5% interest on $102.50, and his new balance will be $105.06. By December, his account will have grown to $110.38. What will the balance be after 5 years? Dave could add 2.5% interest to his first-year balance. This gives him the balance at the end of the first quarter of the second year, which is $113.14. Then he could add 2.5% to that balance to get the balance for the second quarter of the second year, and so on for 20 quarters, the number of quarters in 5 years. But by the time he finishes all those calculations, he may miss the early boat. Luckily for him, he can use the formula we've developed to figure out his interest over any time period with any interest rate. The general version of this formula for geometric growth is P times 1 plus R to the nth power equals A. P equals the initial deposit or principal. R equals the interest rate per period, and N, which is an exponent, equals the number of times the interest is compounded. A is the amount of money in the account after N periods. Now, keep in mind that R represents the interest rate per period, and N is the number of periods. For example, if you wanted to know the accumulation in an annually compounded account after 5 years with a 10% interest rate, R would equal 10%, or 0.1, and N, the number of times the interest is compounded, would equal 5. But in the case of quarterly compounding, R equals 2.5%, or 0.025, and N equals 20 because we're compounding quarterly for 20 quarters, or 5 years. Remember, P equals $100, so the amount of money in the account after 5 years equals $100 times 1 plus 0.025 raised to the 20th power, or $163.86. When we compare this 5-year balance in the quarterly compounding account to the balance in the annually compounding account, you can see that you earn more money in an account that compounds more often. Since you earn interest more frequently, your yield, called the effective annual yield, is really more than 10% of your principal. If the interest were compounded monthly, the 5-year accumulation would be even more, $164.53. Well, it seems like Dave has it made. If he can only find a bank that compounds interest every minute or every second, then he'll really be in the money, right? Unfortunately not. Jim Grebe, an executive vice president at the New World Bank, tells us why.
The biggest incremental impact of compounding is when you take the year and you cut it into 2 pieces. You cut the year into 12 pieces, and you do pick up more interest, but they're smaller pieces. You cut it into 365 pieces, and you pick up more interest, but the daily increments are so small that the difference between compounding monthly and compounding daily, although significant on a big balance, isn't 31 times. It does not work out that way.
Let's say Dave's $100 deposit earns interest that's compounded daily. Here's the result if it's compounded hourly. You can see that the more often interest is compounded, the smaller the increment of growth. Eventually, the size of Dave's balance would approach a limit of $164.87. Here's why. Although no bank gives 100% interest, suppose for a minute that one did. With a deposit of $100, in 1 year it would grow to $100 times 1 plus 100%, or 1, over n raised to the nth power, where n is the number of compounding periods. As n gets bigger, the term 1 plus 1 over n to the nth gets closer and closer to a special number called e. Now, e equals 2.71828 ... The 3 dots mean that the decimal never stops. That means that even at 100% interest, a $100 deposit would reach $271.83 in 1 year and no more, even if the interest were compounded every zillionth of a second. For interest rates less than 100%, like the 10% rate of our fishermen, the limiting value for 1 year is $100 times e raised to the 1/10th power, which equals $110.52, and for 5 years is $100 times e raised to the 5/10th power, which equals $164.87. When we compare Dave's 5-year balance at various compounding rates, we reach this limit in the hourly compounding account. Compounding more frequently doesn't make any difference.
Now, if a bank is doing a good job with their customers, they should be able to explain in pretty clear terms what the balance requirements are, what the penalties are if the account drops below that balance requirement, and how much interest the customer is going to earn. That level of explanation is really incumbent upon the bank and its people to try to make the customer understand which product is appropriate. What the depositor has to be aware of is not to trade off the basic interest rate for more frequent compounding. If, for example, you could deposit funds and earn an interest rate of 9% compounded monthly, you will get an effective 9.38%. If you were to go to an account that paid a lower rate of interest but compounded daily, say even 8.9%, which is only 0.1% lower, compounding daily still wouldn't add up to as much interest as 9% compounded monthly. So So if all other things are equal, and you have the same rate in two different accounts, and one compounds more frequently, by all means, the consumer should take that account. But if one compounds more frequently but pays a lower rate, you might want to very carefully consider the account with a higher rate. Typically, you're better off.
Now that Dave's money is safely earning interest in the bank, Dave can turn his attention back to today's tow. You see, the formula we use to figure out savings growth also applies to the way the fish population renews itself. These two goldfish, one male and the other female, will before long produce about 10 more fish. The 10 will give birth to about 50, which in turn will give birth to 250, and so on. Now, it might seem like this process could go on forever, and that soon there'll be thousands of fish in this aquarium. But there really isn't room enough in the tank for that many fish, and there isn't enough food. Something has to give, and it better not be the size of this tank. Eventually, the rate at which new members are added to the population will level off. When we graph the number of fish in the tank over time, we'll see a period of rapid growth and then a leveling off as the limitations of food and living space come into play. Knowing that the population of fish is limited, the fishing industry has to figure out a harvesting policy that doesn't deplete that population, one that maintains it at a healthy size. We know that a population of fish will naturally grow by a certain amount. So long as we don't harvest more than the population grows, we shouldn't be in any danger of depleting our resource. For instance, say the haddock population normally grows from 100 tons to 125 tons in one season. If we harvest 25 tons of fish, the population size will fall to 100 tons. But by next season, it will grow back to 125 tons. Then we'll be able to harvest 25 tons again, and the cycle of harvesting and replenishing would continue. We can write an equation for this type of harvesting practice, called a sustained yield policy. If X is the population size at the beginning of the season, and Y is the population size at the end, then Y minus X is equal to the amount of natural increase. As long as we limit the amount to be harvested, or H, to Y minus X, the amount of natural increase, we'll satisfy the sustained yield policy. Sounds easy, but the real problem for fishery managers is figuring out what X and Y are. You can't possibly count all the fish in the ocean. What's more, you also need to know what proportion of the population is of harvestable size. Fishermen bring thousands of pounds of fish into this port every day. In effect, what they catch is a sample of what's in the ocean.
And where were you?
We are 43.
Claudia Dennis, a port agent from the National Marine Laboratory, monitors the daily activities at the pier.
We lost a day and a half.
For weather?
A day for weather, half a day for damage to the nets.
From interviews with fishermen, a port agent gathers statistical data such as the location of the fishing, depth of the water, and the total amount of time spent.
Okay, and fishing round the clock? Okay.
Today's catch is weighed and the fish are sold to distributors. But before the fish can be shipped to local seafood restaurants, the port agent selects a sample of 100 fish of one species for detailed analysis. First, she separates the sample into male and female. The containers are then placed on a scale to determine the average weight of each fish. The fish are measured for length. Age is determined by removing the ear bone. An ear bone has ridges which form annually, much like the rings on a tree. The National Marine Laboratory uses the statistics of the catch, plus the age, sex, and weight of the sample to determine X, the original population, and Y, the population at the end of the season. Once values for X and Y have been collected for many seasons, they're used to make a graph called a reproduction curve. Let's make a reproduction curve with the X and Y values we used for the haddock population. We'll plot the population size at the beginning of the first season, 100 tons, on the X-axis of the graph. We'll then plot the population size at the end of that season, 125 tons, on the Y-axis. Now, assuming we don't harvest any fish and that none die, the population size at the beginning of the second season, X, will be 125 tons. So the Y value for the first season becomes the X value for the second season. At the end of the second season, the population has grown to 160 tons, the Y value. We repeat this procedure many times until we have enough points to draw a smooth curve, which we'll use to determine the harvesting policy. Every point on this curve represents both an X and a Y value. Remember, the equation for a sustained yield is Y minus X equals H, where H is equal to the amount of fish we should harvest if we want to sustain our yield. Here, X equals 125 and Y equals 160. So the sustainable yield is therefore 35 tons. This means that if the population grows from 125 tons to 160 tons in one season, we should harvest 35 tons to sustain our yield. There's an easy way to find H without doing any calculations at all. Draw a 45-degree line from the origin of the coordinate system, the point at which X equals 0 and Y equals 0. For every point on this line, the X and Y values are always the same. The distance between the line and the curve is equal to Y minus X, or H. Stated another way, the height of any vertical segment between the dashed line and the curve will give us H for the X and Y points represented by that part of the curve. Now, an interesting thing is happening. If we move along the curve from left to right, we see that H at first increases and then decreases. That makes intuitive sense. As the population increases, so do the sustainable yields. As the population levels off, the sustainable yields decrease. Initially, the fish population grows geometrically. Every season, the amount of growth increases. But then the amount of growth starts to level off, as environmental limitations, like the availability of food and living space, come into play. Fishery managers would really like to know which, out of all the sustainable yields possible, is the maximum sustainable yield. In other words, at what population size can we harvest the most fish while still sustaining our yield? If we didn't have a reproduction curve, that would be very difficult to figure out. But instead of floundering around, all we need to do is to find the longest vertical segment between the dashed line and the curve. The length of this vertical segment is the maximum sustainable yield, 60 tons of fish. When we project down to the x-axis, we get the population size that gives us the maximum sustainable yield. Call that value M. In this case, M is equal to 250 tons of fish. So this population size, 250 tons, is the one that allows us to have the maximum catch while leaving enough fish to ensure healthy yields in the future. But there's more to fishing than the size of the population. For every day that Dave goes out, the cost of operating the boat and paying the crew is the same, whether he catches one fish or 1,000. When the yield is high, say 350 pounds, the cost of harvesting is spread out over that many fish. But when the yield is disappointing, like today's 100 pounds, the cost of harvesting is spread out over fewer fish. In other words, Dave's profit dwindles when his operating costs are not offset by the amount of fish he has to sell. In the long run, then, it can be more economical to fish from a larger overall population and make fewer tows, even if that means catching fewer fish. To make sure there's a large enough fish population, the actual harvesting policy calls for taking fewer fish than the maximum sustainable yield. We can incorporate the cost of harvesting into our reproduction curve. The population size which gives a maximum profit is indicated by Q. Notice that Q is larger than M, the population size that gives us the maximum sustainable yield. But the yield itself is smaller. Because fewer individuals are being harvested, the gross profit decreases. However, since Q is larger than M, the savings in harvesting costs more than offset the smaller yield. This results in a greater net profit. The human population, like fish or money in a compound interest account, can also be modeled by geometric growth. Just as we saw with the goldfish, more members are added to the population in the current generation than in the one before it. This counter at the Boston Museum of Science uses census figures gathered by the Population Reference Bureau in Washington, D.C. The rate, updated every few months, combines birth and death rates from individual countries around the world. Right now, 4 people are born and 1.4 people die every second, which results in a net increase of 207,000 people per day. Now, birth and death rates don't remain constant for very long, so care must be taken in making population projections over a long period of time. But for shorter periods, it's useful to ask such questions as what will happen to a country's population size if the rate of growth stays the same. Let's try it for the U.S. population. Using the equation we've developed, let's figure out the U.S. population in 20 years. P equals the number of people in the United States today, 227 million. Let's assume that R, the growth rate, is 2%, and N equals 20 years. Solving the equation, the U.S. population in 20 years will have grown from 227 to 337 million people. Now, what will happen to the population size if we increase the growth rate by a small amount, say half of 1%? Now, R is equal to 2.5%. After 20 years, the population will be 372 million people. With a change in growth rate of just 1/2 of 1%, we get a difference of 35 million people. You can see why it's important for social planners to have accurate predictors of population growth. Just as we saw with the fish population, it's critical to know not only the size of the population, which is accomplished through annual census, but also how that population is distributed or stratified according to categories like age and sex. For example, government planners need to know the age of young people in order to provide adequate education. And in the area of health care, men and women have different needs. The distribution of a population by age and sex together is usually represented by a special type of bar graph called a population pyramid. Each of the horizontal bars represents an age category, the youngest at the bottom and the oldest at the top. The age spectrum is frequently broken down into 5-year intervals. The length of the bar represents, in this case, the percentage of people in each category. This way you can vividly see each age category with respect to every other. Data for females are on the right side of the vertical axis, and data for males are on the left side. This particular pyramid graphs the population of Morocco in 1985. Notice that each age group is larger than the one before it. This type of pyramid is called expansive. It indicates a high birth rate and a population weighted toward the younger age categories. For Moroccan citizens, this means that there are many more young dependents in the society than working-age people to care for them. Now compare Morocco's population pyramid with that of Sweden. Sweden's population is characterized as near stationary. That is, the rate of growth is near zero, and there are roughly equal numbers of people in all age categories. Here's the population pyramid for the U.S. in 1985. Notice that there's a bulge in the lower middle part of the graph, from people born around 1945 to those born in 1960. This part of the graph represents the so-called baby boom. That type of diagram represents the U.S. population at a specific point in time. But remember, populations are constantly changing, not only in size, but in composition. That is, the relative number of individuals in the various age groups are changing. What will happen to the U.S. population as baby boomers age? Dr. Michael Stoto, a populations expert at Harvard University, explains.
Think about what happens when a relatively large number of people are born in 1 year or 1 decade. Well, it starts out that the population age structure is relatively uniform, except for a spike at the very youngest ages. Well, then, a few years later, that spike moves down to the age at which children go to school. And then a few years later, that spike moves down to the ages at which children go to high school, and then college, and then get jobs, and then buy houses. And then when they get older, they need health care. And what you have is a spike that moves down the population structure pretty much the way that you see when a snake is digesting a mouse. The mouse is a big lump that moves down through the body of the snake, and that's very similar to the way that a baby boom generation moves through the population.
Notice the decline in population after the baby boom, and the bottom bar that's longer than the one that preceded it. This increase was due in part to the maturing of baby boomers to childbearing age. This phenomenon is sometimes called the boom on the boom. As baby boomers age, the shifting bulge will have dramatic effects on our social systems. In the year 2000, the oldest baby boomers will retire and become eligible for Social Security benefits.
It seemed very attractive and feasible to develop a Social Security system where the people who were working paid for the people who were receiving the benefits, and they thought that over time they could build up a trust fund to pay for the benefits of the elderly. Now, what's happened since then? Well, first of all, the relative number of elderly has changed. It used to be that there was about I think it was about 10 or 12 working people for every retired person. Now it's something more like 2 or 3. And when the people who were born during the baby boom get older and retire, the relative number of workers to elderly people may be less than 2. The ratio may be less than 2. So there are drastic changes in the age structure of the population, which means that we have to reconsider the way that we finance the Social Security system.
So population growth affects us in ways that aren't always apparent. That's part of the beauty of mathematical inquiry. It draws out structural similarities between ideas and things that on the surface don't seem to be related at all. We now know that money, fish, and humans are very specifically linked. And once we understand how populations grow, mathematics gives us tools to transform raw numbers into a meaningful analysis of our world.